In this lecture, we'll discuss the notion of internal stability. Most of the discussions that we'll do here in general hold for continuous time systems. We'll see specific results with respect to linear systems in this part. So, what is internal stability? Internal stability is essentially a boundedness. It is something to do with the boundedness property or the asymptotic behavior of what? Of the solutions of the zero input linear state equation. So we have been seeing linear state equations of the form x dot equal to ax plus bu. Now suppose the u is 0, which means there is no external input to the system, and the system is left to evolve on its own. Internal stability basically talks of as the system evolves, whether the evolution remains bounded or not. So basically the solution x of t remains bounded or not, and whether there is some asymptotic behavior of the system towards any value. Okay, is it going towards 0 or not, or is it becoming constant, and so on. In internal stability, we'll see three types of internal stability. One is uniform stability or uniformly stable, where it just talks about the boundedness. The remaining two internal stabilities, which are uniform exponential stability and uniform asymptotic stability, they are more concerned with the fact that as time progresses, will the solution x of t go towards 0? Basically, will the system's response in the absence, or whether the system's evolution in the absence of input is such that it is going towards 0 or not. Okay. So we'll start with the first concept, which is uniformly stable, uniform stability. So in all the cases of stability, since we are talking of boundedness and whether things are going towards 0 or not, we'll be focusing on how the norm of the solution is evolving with time. Okay, so if the norm is bounded, then essentially all the individual states in a state vector will be bounded. If the norm is unbounded, then there is at least one state in the state vector which is going unbounded. Okay, so similarly, if the norm is 0, then essentially all the state vectors are 0. Okay, so if the norm is going towards 0 as time approaches infinity, that means all the states in the state vector are also approaching towards 0 as t approaches infinity. Okay, so consider. So we'll set up an axis where t is on the horizontal axis and norm of xt is on the vertical axis. This is any norm that you can, any valid definition of norm that you can think of. So what is this trying to say is, if your initial condition, okay, is x0 at some initial time t0, can I draw a line which is a scaled version of x0 such that if the solution starts at x0, the solution will always remain below the line that I have drawn. So the line that I am talking of is the dashed line. Gamma is the scaling factor, and then you have norm of x0. Okay, so let's say that this red trajectory is what we get as a solution to the norm of to the system that we have in hand, and it is starting with the initial value of x0 at time t0. So initially at t0, the norm is equal, norm of xt is equal to norm of x0. What we are trying to see is it possible to draw a line which is a scaled version of the norm of the initial condition, so that the trajectory's norm remains always below that line, which means this value of gamma norm of x0, gamma being a positive quantity, positive finite quantity of course, is the upper bound on the norm of xt for all time t greater than equal to t0. Okay, which means can the norm of the trajectory be upper bounded? Okay, on top of it, for any value or any initial condition x0 for the same time t0, I should be able to choose the same scaling factor gamma. So let's say my initial state is initial state x0's norm is 1. For that I choose my gamma to be, let's say, 2, for which I see that I'm able to bound the trajectory that is evolving. And if I change my initial state, let's say I change my initial state so that the norm is 0.5, when my initial state is changed to 0.5, I should be able to still show that for gamma equal to 2, whatever trajectory is evolving from this new x0, it can be bounded. Okay, not only this, given any other initial time, if you start at the same initial condition, the same gamma should hold, which means gamma is going to be independent of what is the initial state value that you choose and what is the initial time that you choose. Okay, and using this gamma you will be able to bound the trajectory's norm that is evolving from the initial value that has been suggested and initial time. So to put this thing in writing, what we have is the system 1. 1 is what we are saying, we are considering this LTI system, x dot equal to ax, where a can very well be a time varying quantity starting at an initial condition x0. System 1 is uniformly stable if there exists a positive finite constant gamma such that for any initial condition that you choose, the corresponding solution will always satisfy this inequality, that the norm of the trajectory is upper bounded by gamma norm of x0. Okay, and notice that this gamma is independent of t0 and also of x0, and this has to hold for all t greater than equal to t0. Also note that gamma is going to be greater than equal to 1. It cannot be less than 1. Okay. Now this word of uniform gets associated with this notion of stability. The reason being that gamma is independent of t0. So irrespective of what is t0, you can uniformly choose gamma. You can say that this is the gamma that you need to choose so that the norm of the trajectory remains upper bounded by a scaling factor of gamma, by scaling the norm of x0 with gamma. Okay. You can put this in another way, which basically relates gamma to the state transition matrix of the system. So the system 1, the linear system, is uniformly stable if and only if there exists a finite positive constant gamma such that the norm of the state transition matrix over the interval t to tau, or for two time instants t to tau, is going to be less than equal to gamma. And this holds for all values of t and tau that you can think of, such that t is greater than equal to tau. Okay. For linear time invariant systems, uniform stability is guaranteed if and only if all its eigenvalues, okay, so you have this matrix A, calculate all its eigenvalues. If all of its eigenvalues have non-positive real part, okay, so if you take the eigenvalues and check the real part, none of the all the real parts will either be less than or equal to 0. Okay, that is what non-positive means. With a condition that if you have any eigenvalue on the imaginary axis or any eigenvalue which is purely imaginary, basically those whose real parts are 0, then their algebraic multiplicity has to be 1, which means they should not be repeated more than 1. Okay, there should not be no repetition of purely imaginary eigenvalues. Okay, so to repeat this, if you have a LTI system, and if you are considering the zero input system, then we can say that the system is uniformly stable if and only if all the eigenvalues that we have found out for this system, their real part is either less than or equal to 0, which specifically if the eigenvalues are purely imaginary, then their algebraic multiplicity should be 1, which means they should not be repeated. They should occur only once. Okay. So this basically, if you see this condition, at least for the LTI system, it simplifies the checking of the uniform stability of the LTI system a lot. Otherwise, what you would have to do is, if you go by the definition, you would have to check for the value of gamma being able to bound the norm of the state transition matrix for all values of t and tau. So calculating the state transition matrix might be a little difficult, and similarly you have to check it, you have to establish that it holds for all t and tau, okay, which may or may not be easy. So this condition simplifies things a lot and has been derived from the definition of the uniform stability. Now, what can we say, or what kind of condition can we establish for linear time varying systems? So the notion of uniform stability can also be related to the eigenvalues of linear time varying systems. However, one should also note that since the matrix A is time varying, the eigenvalues associated with the matrix is also time varying. Okay, so for the system 1, where A is a time varying matrix, let us say that at every instant of time we calculate the eigenvalues and we denote the largest eigenvalue of, so we calculate the eigenvalues of A t plus A transpose t, okay, and we denote the largest eigenvalue or the largest pointwise eigenvalue as lambda max of t and the smallest eigenvalue as the lambda min of t. Let's say we do that. Then for any x0 and t0, so for any initial condition and any initial time, the solution of equation 1 always satisfies this inequality. Okay, at every time t, this is what will always be satisfied. So on the lower bound, it is related to the smallest eigenvalue. On the upper bound, it is related to the largest eigenvalue which have been calculated pointwise. Okay. Now, this system with a time varying matrix is uniformly stable if there exists a positive constant gamma such that, now this gamma and the gamma that we had said or expressed there are essentially different. Okay, so I should be able to find a positive finite constant gamma such that the integration of lambda max over the interval tau till t for all tau t and t greater than equal to tau should be less than equal to gamma. Okay, if this holds, then my system is uniformly stable. Okay, so here in fact it may or may not be easy to establish this because the lambda max and lambda min keep on changing, and it may so happen that we do not have a specific expression for lambda max and lambda min. Now notice one thing about the uniform stability. It just imposes that the solution remains bounded. You should be able to find a gamma so that it helps in setting up a upper bound with respect to the with the help of the initial condition. Okay. Now this gamma, as I said, has to be a finite positive constant, so it ranges anything between 1 to infinity, infinity of course excluded. So this gamma can be very high, thus giving us probably a conservative bound when we calculate using these conditions. Okay. Also, it does not say that whether the solution is going towards zero or not, whether the state vectors are decaying to zero or not, which is of interest in most of the cases, or is it going towards a constant value or not. Okay, so this is not being imposed by the uniform stability. So this is where another concept of stability comes in, which is uniform exponential stability. Okay. So what is uniform exponential stability? So consider the system that we have in hand, and we start with initial condition x0 at some time t0. So as the system evolves, okay, the trajectory may possibly look like the blue trajectory that we have in hand. Okay, what exponential stability or uniform exponential stability says is you can upper bound or you can draw a exponential curve on top of the evolving trajectory. When I say evolving trajectory, I'm basically talking about the norm of evolving trajectory. If I can draw exponential curve on the top of the norm of this trajectory, this blue curve is the norm of the trajectory. You can draw exponential curve which is shown by a red line or the red sketch here. Okay, for all time t. Now, because the red sketch is an exponential curve, as t approaches infinity, the red sketch is going to 0. And we are saying that I have been able to draw this red sketch such that it always remains above this blue sketch. This blue sketch is actually representing the evolution of the system. So that means as time progresses, the magnitude of the blue sketch is going to decrease and eventually go to 0. So this is what exponential stability means. The word uniform comes in because the constant gamma that you see here and the rate at which this exponential trajectory is evolving, let us say that that rate is lambda, are independent of the initial time t0. Okay, in fact, if you start at some different time t0 dash at the same initial condition x0, there is the same exponential curve that can actually upper bound the trajectory that is evolving. The evolution of the trajectory may be different, but the same curve can actually upper bound it. Okay, so the decay rate of both the curves in this case should be gamma, and they start at decay rate will be lambda, and they start at a point gamma norm of x0. And put it formally, we call the linear system with zero input to be uniformly exponentially stable if we have finite positive constants, namely gamma and lambda, such that for any initial time t0, this relationship, this inequality is satisfied. So the norm of the trajectory that is evolving x of t is always upper bounded by a exponential curve multiplied by norm of x0, and this is true for all time t greater than equal to t0. Okay, this essentially indicates that the norm at best can decay at a rate of lambda. Okay, so we can also establish the decay rate. In some cases, we can control this decay rate by suitably placing the eigenvalues, at least for LTI system. Now, here also note that the gamma is going to be greater than equal to 1, whereas the lambda is going to be greater than 0. If lambda is equal to 0, what you essentially have is uniform stability. In other words, if I want to relate these conditions to the state transition matrix of the linear system, then the linear system with zero input is uniformly exponentially stable if and only if there exist finite positive constants gamma and lambda such that the norm is less than the exponential constant, which is gamma e power minus lambda t minus tau. Okay, and this has to hold for all t and tau with e being greater than equal to tau. Okay, so the norm of the state transition matrix has to be bounded by the exponential curve given by gamma e power minus lambda t minus tau. Okay. Now for linear time varying systems, in fact this will hold for time invariant systems as well. For linear time varying systems, we can say that it is uniformly exponentially stable if there exists finite positive constants gamma and lambda. Now this gamma and lambda are different from the gamma and lambda that we discussed upstairs, such that the integration of lambda max over the interval t to tau is less than equal to this particular expression on the right hand side of the inequality. Now notice that if lambda is 0, then you essentially end up with the condition that you saw for the uniform stability of this system. Now if you have this, then essentially you end up showing that it is uniformly exponentially stable. And this has to hold for all t tau with t greater than equal to tau. For linear time invariant systems, if we want to relate it to the eigenvalues, what it means that all the eigenvalues of A should be such that the real part of all the eigenvalues are all negative, meaning they are all less than 0, they're strictly less than 0. None of the eigenvalues will have a real part which is 0. Okay, so LTI system x not equal to Ax is uniformly exponentially stable if and only if all eigenvalues of A have negative real part. Okay, so this is because as we recall, as time progresses, all negative real parts will ensure that they go to 0. So now we'll move on to the third concept, which is basically uniform asymptotic stability. So uniform asymptotic stability is a stability notion which is somewhere in between uniform stability and uniform exponential stability. So it is a little stricter than uniform stability because it needs the trajectories, or it ensures that the trajectories will go to 0 as t approaches or as time progresses, while it is a weaker condition, or it is a relaxed condition with respect to uniform exponential stability, with reason being that it does not impose any exponential decay rate on the solution that we have. Okay. So in general to speak, uniform asymptotic stability is stricter than uniform stability, but is relaxed as compared to uniform exponential stability. So what does this say? We'll first look at the statement and then we'll see at a sketch that tries to explain the statement. So the linear system with zero input is said to be uniformly asymptotically stable if the system is uniformly stable to start with, and on top of it you have one more condition imposed, which is for any finite positive constant delta that is given to you. So someone, let's say, comes and tells you that this is the finite positive constant delta that you are supposed to choose. Delta is greater than 0, of course. Okay. What is the purpose of delta will get clear. For any given finite positive constant delta, you should be able to find a finite positive variable, finite positive constant t, capital T, such that for any initial time that you start with, okay, if for any initial time that you start with, the norm of the evolving trajectory, so the norm of xt is going to be less than equal to delta times norm of the initial condition for all t greater than equal to t0 plus capital T. What this means is, if I am given with a value of delta, I should be able to tell that after what time from the start will my norm of the trajectory be bounded by delta norm of x0. So let's say that someone tells me that my x0 is 1, norm of x0 is 1, and suppose someone gives me that delta is 0.5. I should be able to tell them that if my system started at, let's say, t equal to 0, I should be able to give them a time after which my norm of xt will be less than 0.5, which is delta, into 1, which is norm of x0. After what time it will hold. And this I should be able to do for any value of delta is given. So if I give it for 0.5, it doesn't stop there. Someone can come and tell me that, okay, give me a time when delta is less than, when delta is, let's say, equal to 0.001 or 10 to the power minus 3. In that case also, I should be able to come up with a time. Let's say that the time after start is 1000 seconds. After 1000 seconds, I can ensure that norm of xt will be satisfying this inequality. Okay. So no matter what value of delta, how small the value of delta is, until it is costly, I should be able to come up with a time t. Here you should notice that the capital T, or the time after which the inequality will be satisfied, always depends on the value of delta. Okay, it is independent of when you start or what is the initial value you start. It depends just on what is the value of delta that is being given to you. So if you draw a sketch, let's say that you start your system at some norm of x0 at some initial time t0, and let's say that this is the trajectory that is evolving with time. Now let's say that this is a trajectory such that I cannot draw uniform exponential, I cannot draw exponential curve right on top of it. Okay, so I'm speaking in general. Now someone gives me a constant value, let's say delta 1. So if I see delta 1 norm of x0, the red line represents the value where it represents delta 1 norm of x0. Okay. What is the time after which, or will I be able to find a time after which my trajectory has a norm less than delta 1 norm of x0? Answer is yes, and this is the time. And I'll label this as after t1 time, or after t1 span of the time, my trajectories will always be less than the given delta 1 norm of x0. So you will always lie below the line. Now someone gives me another value, let's say delta 2, which is much smaller than delta 1. So what is the time after which my trajectory will always be below this green line that I have drawn? In this case, it turns out that there is a time t2. Now I should be able to do this for any value of delta that is being given to me, any non-zero positive value of delta that is being given to me, no matter how small the value of delta is. So because I will be able to do this no matter how small the value of delta is, that means that my trajectories are slowly approaching 0. Okay, so this is what is the definition of uniform asymptotic stability. So it so happens that, and this has been established in various books, we will not go through this proof, but it so happens that for linear systems, uniform asymptotic stability and uniform exponential stability are equivalent statements, which means if a linear system is uniformly asymptotically stable, then the linear system is also uniformly exponentially stable. So if someone gives you a linear system and says that this is a system which is uniformly asymptotically stable, then you can right away say that, oh yes, then this system is also uniformly exponentially stable, which means you can draw a exponential curve, decaying curve right on top of the evolving trajectory. Okay. In general, if the system is not linear, UAS will not imply UES. So UAS is uniform asymptotic stability. It will not imply UES or the uniform exponential stability. Okay. However, uniform exponential stability essentially implies uniform asymptotic stability. Okay. The reverse implication does not hold. That uniform asymptotic stability will not imply uniform exponential stability in general if the system is not linear. For linear systems, this is a bidirectional implication. So uniform asymptotic stability and uniform exponential stability are essentially equivalent. So we'll stop with this notion here. Thank you.